Okay, we are going to talk about something that we're going to talk about something that, without judging you, I automatically assume, which is kind of makes me a terrible person, but that's fine. I automatically assume that every single person in here has a little bit of experience with. Right? Yeah.
I don't.
With alcohol?
Yeah. I'm assuming that when every single one of you was about, like, maybe 4 or 5 years old, that kind of thing, I'm assuming every single one of you, at least by then, had your first interaction with alcohol. No. Wow, that's not where I was going with this at all.
Come on.
No.
Rubbing alcohol.
Yeah, you've never used rubbing alcohol before?
Oh, some of that. Okay.
I thought you
were do Hydrohalogenation.
It's okay. We know the underlying.
No.
Just kidding. It's okay. We made it.
Alcohols are compounds with a different functional group. So now we have 2 functional groups in our list. And I need you, it's probably pretty easy to recognize the difference between them so far. What's the only other functional group other than alcohols that we've talked about? Halides, the halogens, right? Organic halides, alkyl halides, halogenated hydrocarbons, whatever. There's many different names for them. The point is that if something has a fluorine, chlorine, bromine, or iodine on them, then it's a halogenated hydrocarbon or alkyl halide. This is different. What? You could test the alcohol, but in most cases it'll make you dead, or something close to that. Okay? Alcohols are compounds with 1 or more hydroxyl group, and this is I feel bad because it's split up. It's an ROH, where R represents any hydrocarbon at all. So the OH is attached to a carbon, and then that carbon is attached to a bunch of other crap. So for example, I'm going to draw a chemical, and I want you to tell me yes or no, does it have a hydroxyl group on it?
What do you want me to do?
I do. Whoa, that's a big one.
That's like a little too big there. What I'm just saying. Very big.
All the options.
Wow. Looks like a.
Does this have a hydroxyl on it?
Yes.
Yes. How easy was that to spot? Very easy, right? I'm gonna draw this a slightly different way, and it's probably gonna make some of you mad at me, and that's totally fine. Whatever, it doesn't really matter. I'm gonna kill you. Does this have a hydroxyl on it?
Yes.
No.
Oh wait.
Now, I know you should be angry at me. The combination of a C double bond O and then attached to an OH is a totally different, completely different functional group. This thing behaves completely differently than just an OH. Okay? If you guys have to go somewhere, then go ahead and go somewhere. I'm kind of in a bad mood. So if I'm short with you, then I apologize. I just don't like having my time wasted by people, that's all. So this is an alcohol, but that's not, and we'll learn more about those hopefully tomorrow. That's called a carboxylic acid. This is an alcohol or a hydroxyl group. Okay? Hydroxyl groups add to the ability of hydrogen bonding in molecules, affecting both the solubility and the boiling point. Most of you, all joking aside, most of you are probably really familiar with 2 alcohols, okay? There's ethanol, which is in compounds that people imbibe, right? That's the active component in alcohol. We call it alcohol even though it's really ethanol that's in there. Now what would ethanol look like?
2 carbons.
2 carbons with a what attached?
Hydroxyl.
Yeah. And so we say ethanol. We say ethanol. And so you can see how, well, there's 2 carbons. Are there any double bonds in here? No, because it's an, right? It's an alkane. And then the all indicates the presence of a hydroxyl group or an alcohol group. That's probably one that people are really, really familiar with. There's another one called isopropyl alcohol or 2-propanol. So if I said, or like we could call it propan 2-all. So propan 2-all. Could you, without really even learning anything from me today, could you draw me the structure of propan 2-all? How many carbons are in propan 2-all? 3 carbons. What's the one only functional group that you see on propan 2-all? It's an all, so it's an OH. And where is it attached to?
2.
Carbon number 2. Does this system of naming kind of make sense? Yeah. The reason why we didn't put the 2 at the front is because we might have other like methyl or ethyl groups on here as well, right? And so we say propan 2-all, indicating that the all, the hydroxyl group, is on carbon number 2. Max, your hand was up.
It was up because I got confused as to why the 2 didn't mean a double bond, but then I realized it's because the suffix was different.
Yeah, it would be propene 2-all, right? Yeah. So just as long as you understand. Alcohols are named similar to other organic compounds, except we start numbering closest to the hydroxyl group. So this functional group, the hydroxyl group, it now takes priority over the double bond. Now, I've never, ever seen a naming problem on the diploma where you had both an alcohol and a double bond. I've never seen it, and I highly doubt you'll ever see it. If they want to see whether or not you know how to name an alcohol, they'll just give you a straight up alcohol, maybe with some branches on it, that's all. We dropped the E from the end, so hopefully you've noticed it's not propane 2-all, it's propan 2-all. And I don't know why that is. I really sincerely don't. I think it's just they had to decide an arbitrary set of rules and they decided, let's add another rule on here. Sorry. Drop the E from the end and we add all. Specify the carbon the hydroxyl is attached to. If the alcohol has more than one hydroxyl group, don't drop the E. And then tell me where they both are and say diol, triol, tetraol, that kind of thing. So let's try a couple. I would like you to draw for me 3-methyl-butan 2-all, and then also pent 2-ene 1,3-diol. Go ahead and draw them, just because I feel like you can. I have lots of confidence in your abilities. Yes. Straightforward?
Yep.
Yep. Yes. They're both mean the same. Yeah. Yes. As long as you fill in the idea. Just because you drew the carbon separately, so now you have to draw. Yeah. Or you could have done a condensed diagram. You could have just attached the hydrogen switches. How many carbons are there? I don't know. Very close. Do you want me to draw a condensed diagram or a line diagram?
Structural.
Okay, I'll draw both. I'm not going to draw a structural diagram. Just because I do not want to waste my time. Okay, so let's do a condensed diagram. So how many carbons in a row? How many carbons in our parent chain? 4. 1, 2, 3, 4. And where's the methyl attached to? 3, so CH3. And where's the all attached to? 2, so OH. Now I want to be very clear. You can say OH as long as you understand that it really means an O bonded to an H, right? That's what it really truly means. OH is an O bonded to an H. We have to write OH so many times that there's no point. So we say OH, as long as you understand. So OH, and then we'll just fill in the rest of the hydrogens. 3 here, 1 here, 1 here, 3 here. So that's the condensed diagram, the line diagram. 1, 2, 3, 4, and we've got a methyl group coming there, and we've got an OH there. Perfect. That's how I would draw those. How many carbons in this parent chain? 5. So 1, 2, 3, 4, 5. And where are the alls on? Where's the OHs on? 1 and 3. So you could say OH, right? Off the 1. Or you could have, whatever, it doesn't matter to me. You could have went down OH. And then where's the double bond? Where does it start at? 2. So it goes from 2 to 3, right? So then you just fill in all the hydrogens, CH2, this one can only have 1 H, that one can't have any, that one can have 2, that one can have 3. So you could have done that. Or you could have done the line diagram. 1, 2, 3, 4, 5. And we've got an all here. We've got an all here. Now here's the problem. Whenever you draw a line diagram, or whenever somebody draws a line diagram, and then they attach stuff to that carbon, a lot of people start counting their carbons. Instead of here, where the first carbon is, where do they start counting? At the hydroxyl. Is that a carbon? No, it's an O. It's telling you it's an O, right? It's an O attached to a carbon. So our double bond has to start at the second carbon. It'll start here. So this is our double bond, right? But people want it to be here because they think that's where the second carbon is. Just by looking at it, they say, first line, second line, that's where I should put it. But that's not where you should put it. As long as you understand that. Did anybody take a stab at naming these?
Yes.
Yes? Okay. So do you want to give me your answer?
2 methyl and 2 all.
So 2 methyl what? 2 methyl what?
2 methyl and 2 all.
2 methyl pentan. Right? Because you haven't indicated if they're all single bonds or double bonds or triple bonds, right? Pentan 2 all. Good. So I could have started numbering from the left or from the right, but because the all is closest to the left, that's where I started numbering from. Now the other one's a little bit of a pain in the buttocks, but that's fine. What's your longest parent chain? 4. So this is going to be butan, and there's not multiple alls, so it's not butane, it's just butan. So where's the hydroxyl attached to? 2. Carbon 2, right? Not carbon 3, it's attached to carbon 2. So butan 2 all, and then what kind of branches do we have on here?
2, 3 dimethyl.
Yeah, that's our parent chain. So we've got 2, 3 dimethyl. So 2, 3 dimethyl butan 2 all. Good to go? Yeah. Okay, so that's naming. All right, naming is a small part of this. What we really care about are the physical and chemical properties of these alcohols. That's what we really care about, okay? So a physical property is some characteristic of this chemical without having it react with some other things. The properties that we care about are solubility, so whether or not it can dissolve in certain things, and then we also care about boiling point. That's kind of the big ones. The hydroxyl group of alcohols gives the compound the ability to hydrogen bond. So what does that mean? Does that mean it's going to be more soluble in water or less soluble in water? More soluble in water. Hopefully that makes sense. Short chain alcohols are very soluble in water. Let's look at this. This is what I mean by a short chain alcohol. It's an alcohol attached to a very short chain of carbons. Is ethanol, remember drinking alcohol, is ethanol soluble in water?
Yes.
Yeah, absolutely. If you pick up any spirit from an alcohol store, a beer store, liquor store, whatever, like vodka, rye, whatever, it's going to be 40% by volume. It's going to be 40% alcohol dissolved in water. Okay, so it seems like it's quite soluble in water, right? This thing is very soluble. The reason why is that this part of the molecule can hydrogen bond with water. The rest of the molecule actually doesn't like to hydrogen bond with water. It doesn't like to, okay? And the reason why that is, I'm just going to draw a picture if that's okay. I know we're going to spend a little bit of time on this, I understand that. But HOH, and that can hydrogen bond to another HOH, which can hydrogen bond to other HOHs. Okay, so in here, we've got 3 molecules of water. Here's one molecule of water, here's another molecule, and here's another molecule. Now, these molecules of water are super attracted to each other because of this hydrogen bonding. Now, in order for something to be soluble in water, it has to kind of break apart these hydrogen bonds. It has to fit in between. If you think of like you and a really cohesive group of friends, in order for somebody else to break you apart, they have to be just as cohesive into your group. Does that kind of make sense? Okay? So in order for something to be soluble in water, it has to be able to what? Hydrogen. Has to be able to hydrogen bond. So if we have this alcohol group, right? The hydrocarbon attached to OH. Can this thing fit in here and start to hydrogen bond with the other water molecules? Yes, it can. Totally it can. Let's draw a different organic molecule. This is a straight chain hydrocarbon. Does it have the ability to hydrogen bond? No. So when it tries to fit itself in, is it strong enough? Is it strong enough to break apart these water molecules from their friends? No, it's not strong enough. Okay? So what happens here is that in order for something to be soluble in water, it has to be equally as strong or attracted to the other waters that are surrounding it. Max?
Wouldn't like if say like your pentane there,
yeah,
or no, your propane there,
yeah,
it bumped into the hydrogen bond. Would the hydrogen from the carbon be attached to the oxygen of the hydrogen bond because the hydrogen bond is stronger than the carbon hydrogen one? Or I'm assuming it it doesn't, but I don't know why.
You're saying would the hydrogen leave this molecule? No, and that's because these are intermolecular bonds. Intermolecular bonds are always weaker than intramolecular bonds. So this carbon has a super strong hold on its hydrogen, okay? It's just how attracted is this to its friends that it surrounds. That's all. Okay, so let's take a look at this. Alcohols are really interesting because one part of the molecule, can one part of the molecule hydrogen bond with these waters?
Yes.
But what about the other part of the molecule? No, it can't. So this is only really soluble. Why? Why is this compound really soluble? Because the part that doesn't like water is tiny. So this attraction can overcome the non-attraction there. But what about this? Here, this part again, right? That part can hydrogen bond. But what about this part? No. So which one of these is going to be more soluble in water? The tiny one, the one with the teeny tiny little hydrocarbon end, right? This part is not soluble, and so this makes it, overall, this molecule is less soluble than that one will be. I don't know, hopefully that makes sense. Predict which molecule will be more soluble in water, and then predict which molecule will be more soluble in cyclohexane. Go ahead, try this out. Take a couple minutes and talk to your friends about it. Because this is important.
Yeah, but it's yeah.
Can I please get a double check? She's at home.
I don't know.
If you're solving whatever. What? No, I'll kind of show you why that is. Okay?
And I don't like the correct
Yep. Yeah, they all have H's on it. Okay. Let's take a look at this. So which one's going to be more soluble? Remember, water looks like this, right? Pentane looks like this. 1, 2, 3, 4, 5. Butane 1,4-diol looks like 1, 2, 3, 4 with an OH and an OH attached to it. Sure, no problem. So, in order for something to be soluble in water, it has to push in between its water friends, right? Which of one of these will be able to force its way into its water friends? The butane 1,4-diol, right? The reason why that is because in general we say like dissolves like. Do you know what I mean? Have you ever heard that before?
No.
Like dissolves like? No?
No.
No?
Yes, you have.
Yes, you have. Okay. Yes, guaranteed you have.
No.
So what like dissolve like means is that if water has the ability to hydrogen bond, then really only other substances that can also hydrogen bond will be able to force its way in between the water molecules. Let's take a look at cyclohexane. What's the structure of cyclohexane?
Stop sign.
It's not, a stop sign is an octagon, not a hexagon. Okay, let's look at this. Can this hydrogen bond? No, it can't. This can't hydrogen bond, right? Okay? So what that means is that if it can't hydrogen bond, then only substances that also can't hydrogen bond will be soluble in it. So the pentane will be more soluble in that. Okay? And I just want to show you, a really quick video that kind of proves this. Kind of proves this.
Ever since then, I've gotten
Stay away from
We're going to look in this presentation at the solubility of iodine in a various numbers of solvents. So the first solvent is dichloromethane.
Okay, I just kind of want to show you.
Dude, this guy's talking.
So what's going to happen here is we're going to add iodine to a couple different layers. One of these solvents is mostly a hydrocarbon. One of these solvents is not a hydrocarbon at all. And so I'm just going to mute him because I forgot how poor the quality was on here. Yeah, I don't know. I think I turned off closed caption. And so what he's doing is he's adding two different solvents. I don't know if you can see it, but can you see two very discrete layers?
Yeah.
The bottom one is cyclohexane. The top one is the bottom one is dichloromethane. That's just an organic solvent. It's a little bit polar, but for the most part, it's not polar. The middle one is water, and then he should be adding another third layer here. Yep.
Oh, that's crazy.
So he's got three different layers of solvent on here. Okay, and the one is not. So he's got cyclohexane on top. He's got water in the middle. And he's got dichloromethane.
Is adding iodine.
And he's adding chunks of iodine. Now, what I want to bring to your attention, I hope I can do this. Yeah, that's what I'm talking about. Okay, so iodine is I2. I'm curious, can this hydrogen bond?
Yeah.
No, it can't.
I don't know. Can it?
No, it can't.
It cannot hydrogen bond. Why? There's no hydrogen, nitrogen, hydrogen, oxygen, or hydrogen fluorine bonds here. Okay? Is this a polar molecule?
No.
No, it's not a polar molecule. It's totally symmetrical, right?
Yes, sir.
And so because it's totally symmetrical, this is a non-polar molecule. You expect this to be able to dissolve in other non-polar molecules. Okay? So let's observe what happens when we add the iodine into the three layers.
This is a chunk.
This is a chunk of iodine. It's a solid chunk of iodine. Is it dissolving in the first layer?
Yes.
It's because cyclohexane is also a non-polar solvent. Non-polar dissolves non-polar, right? Okay, good. What's happening when those iodine chunks hit the water cyclohexane barrier?
It's not good.
Yeah, they're not. Iodine is more dense than water. It should drop, right?
Would be. That's
You okay, Aiden? Yeah, bro. So is the iodine dissolving in the hydrogen bonding layer?
no.
No, because it cannot hydrogen bond.
And that's
Right?
why pentane is able to
What's he adding now?
be soluble in cyclohexane?
No, he's just pouring it into a container. That's all he's doing.
That's his trash.
That's his trash container, yeah.
Ooh.
Yeah, so that's all he's, anyways,
Why
whatever.
do we gotta see his trash?
What?
We want to watch his trash bin.
No, we don't want to watch his trash bin container.
Contain a soluble in cyclohexane.
That's exactly right, Santa. Okay? Yeah, totally right. So, because pentane, let's take a look at pentane. In essence, pentane looks like this, with hydrogen surrounding it in every direction. Is this a polar or non-polar molecule? It's non-polar, so it will dissolve in a non-polar molecule. But the butane 1,4-diol, CCCCOH, this is both polar, but more importantly has the ability to hydrogen bond. So this is partnered up with itself so strongly that the hexane doesn't have enough attraction to break up this and its friends. Right? So they'll never mix. They'll never dissolve with each other. Does that kind of make sense? Yeah, like dissolves. All right, good talk. Okay. Okay, now we're getting to the most important part of today.
Elimination.
Elimination reactions. This is reaction number 3. This is the third type of reaction out of 6 reactions that we have to cover in this unit. And again, I want to be very clear. The reactions and the identifying functional groups are the most important part of this organic chemistry unit. We've done naming and we've done drawing only to get you familiar with the different types of compounds. They may ask you maybe one naming question, but they guaranteed will ask you at least 4 or 5 reaction questions. Okay? So this is the most important part. That's why I put this up here. So yes, do you agree we've already covered addition reactions? Yeah, 2 things turning into 1 thing, good. Do you agree we've also covered substitution reactions? 2 things turning into 2 things. Now we're starting to talk about elimination reactions. That's where, in an elimination reaction, I don't have any more fancy way of saying this, but basically, you're taking a molecule and you're eliminating part of it. Sorry, I know. I know I could have sent that to somebody, but my grade 9 connections kids didn't want to, so tough luck. Yeah, what a bunch of losers. Sorry, Austin. Sorry, Anthony. Sorry, Amy. You're not losers. There's 3 types. There's 3 types of elimination reactions. You do not have to know their names. You do not have to pick them out of a crowd. But you do have to recognize that they are all elimination reactions. Okay? So, cracking is where you take a hydrocarbon and you rip some hydrogens off of it. Dehydration. What happens if you are dehydrated? What has left your body? Water. That's interesting. And then dehydrohalogenation. I'm curious, what 2 elements do you think are leaving in a dehydrohalogenation? No, what 2 elements? Not what you said. Hydrogen and a halogen. Any of the halogens. Send it.
So, are we ever going to be dealing with something where, like spectator ions, like?
Spectator ions don't react.
Okay.
Right?
Yep,
So
I knew
they're
that.
they're bouncing around,
Yeah.
but they're not actually doing anything.
No, I knew that.
Right? Yeah. Okay.
Yeah.
So elimination reactions, the key thing here is they make
Egg, double donuts. Double, triple donuts.
addition reactions use up or break double and triple bonds. Elimination reactions make double or triple bonds. They are the exact opposite. Elimination reactions and addition reactions are the complete opposite of each other. So let's take a look at this. Cracking removes hydrogens from adjacent carbons and produces an alkene and a hydrogen gas. Okay, no problem. So what we have this alkane, and under high temperatures, but you can't have oxygen in here. Why? If I had a really high temperature and I also had oxygen, what would happen?
Evaporation.
No, you would burn this hydrocarbon. You would combust it, right? This takes high temperatures, but no oxygen can be in the container. So what's going to leave here? 2 hydrogens. These 2 hydrogens, or maybe these 2 hydrogens, or maybe these 2 hydrogens.
It can be across the road.
It can be across the road because remember, this is something that I've been using for my Chem 20s, but really, ethane looks like this: 2 carbons attached to each other, and then the hydrogens are the greens and the reds. So it doesn't really matter. There is no hydrogen sticking straight out. There is no hydrogen sticking straight out this way. That's just a 2-dimensional representation of a 3-dimensional object. So this hydrogen, and that hydrogen, they're equally as far apart from these hydrogens. Are we okay with that? Yeah. So when these hydrogens leave, what are we left with?
Double bond.
C, C, H, 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 H. And you can't have anything other than a double bond. It doesn't just, there's no other way to have it plus H2 gas. Jordan.
How come 2 hydrogens?
What?
How come 2? Is it because, why do 2 hydrogens leave? Because if you, because, okay, I just saw.
Good? All right. Good talk. You gotta go, you gotta go. All right. Methylpropane is cracked to produce hydrogen gas and an alkene. I would like you to just try it, okay? Just draw 2-methylpropane, and then crack it, and see what you get. No, you don't get crack cocaine.
That's insane.
I actually have significant hearing problems, but every once in a while it
I
just
said that so quiet.
it just bounces off of somebody's forehead or it bounces off of somebody's wall or something like that. Works out really well.
So his mouth trick shot it.
Yeah.
Through his voice.
No. You're missing a methyl group on there. Okay.
Is that a triple bond?
Wait, no. Oh, wait. Okay. Where do we have hydrogens beside each other? Could it be here and there?
No.
Are those hydrogens beside each other? Sure. What? Yeah, that seems fine with me. What about here and there? Are those hydrogens beside each other? Yeah, sure. Why not? What about here and there? Are those hydrogens beside each other? Those hydrogens, they're not. They're 3 carbons away from each other, right? So no, those wouldn't work. Pick any two hydrogens that are beside each other. Maybe this one and this one, right? The middle one has to be involved. So what are you gonna get? You're gonna get carbon, 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 and now where's the double bond? The way where I drew it, it's here. Right? So now what's left? How many hydrogens are left up on the top carbon? 2, CH2. All right. How many hydrogens are left on the middle carbon? None, right? CH3, CH3, and because we remove 2 hydrogens, boom, Bob's your own. Okay, how could you recognize this as an elimination reaction?
It makes 2 things out of 1.
It makes 2, you've got 2 products from 1 product. That's probably the fastest way to identify it as an elimination reaction. What's the next fastest way? Single bond into a double bond. Saturated into unsaturated. Yeah.
I just have a question, like, I don't know if this is illegal, like what I did here.
No, that's fine. Are these hydrogens attached to carbons that are beside each other?
Yeah.
Correct.
All right.
Okay. That's cracking. This is, what do we call this? Dehydration. So what's going to leave? A water. Now, I want to be very clear that this is going to leave, and you're going to need an acid catalyst for this to happen. Now, that doesn't matter. You don't need to know that. But as long as you can recognize this as an acid catalyst, that's okay. The OH, the alcohol group, is going to leave, but what does it have to take with it in order to turn into a water? A hydrogen. So both of these things leave, and what are we going to form in between the carbons? Double bond. So we get carbon double bonded with carbon. Perfect. So we can make ethene by dehydrating ethanol. Jordy. No, it wouldn't. I'm trying to show you that the hydroxide and the hydrogen left, and that there's a double bond here now. What?
Because you know how double bonds can
Correct. Double bonds cannot spin.
So then,
if this was a university class where we really super duper cared about the shape of our molecule, I would go. There's approximately 120 degrees between all of these bond angles. So, yeah.
How do you dehydrate a liquid?
If you had pure alcohol, like pure ethanol, and I added really super concentrated acid to it, then what could happen is that this attaches to that, the water leaves, then that hydrogen becomes the new catalyst, and then we form a double bond.
How would you separate it?
How do you? No, you wouldn't have to. You wouldn't have to, because what state of matter is alcohol at room temperature? It's a liquid. What state of matter is ethene, which is very closely related to acetylene or ethine? It's a gas.
so the water would just stay.
So the water would stay, and as you make ethene, it would bubble off. So you just got to put like a funnel on top of your beaker, basically, and then just capture the gas.
But then wouldn't sort of acidic water? Wouldn't the acid still be in the water?
The acid and the water would remain in your alcohol, and so what you would do is you would probably add a drying agent to capture the alcohol. Like, this is complicated chemistry right now, but you would add some sort of a compound that captures the water, and so you'd only have the alcohol and the acid constantly reacting, and then the water would constantly be captured, and the ethene would constantly bubble off, and then boom. Okay, let's try the next one. 2-methylpropane 1-ol reacts in an acid catalyst to produce water in an alkene. We're gonna do this one together, and I want to show you. Using a condensed diagram again. So propane 1-ol, so carbon, 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 but it's a 2-methyl. So attached to that number 1 carbon is an alcohol group. So what's going to happen is this alcohol is going to leave. but what's it going to take with it?
Hydrogen.
A hydrogen. Well, where does the hydrogen have to be attached to?
Another carbon.
It has to be attached to the carbon that's beside the carbon it's attached to, right? So they have to be attached to different carbons. So this hydrogen is going to leave as well, and we're going to be left with carbon attached to a carbon attached to a carbon that's double bonded to another carbon. Hopefully that makes sense. It's these carbons attached to that central carbon, with the central carbons attached via a double bond to the other carbon. So if only the hydrogen and the hydroxyl group left, what do we left? What's still attached to this final carbon here? Two hydrogens, right? What's still attached to these methyl groups? The 3 hydrogens. They haven't left. They haven't gone anywhere, right? And then plus H2O. Yeah, I don't know. See, like, it might be complicated now, but all it takes is a little bit of practice. That's what it's going to take. It's going to take a little bit of practice. Okay, we're really close. We're really close. Here we go. Finally, for the last one, dehydrohalogenation. What's happening here is this process uses a strong base to eliminate water and a halogen ion and produces a double bond, okay? So what's going to happen is this, again, this is really complicated chemistry. I kind of wish it wasn't in your curriculum, but that's fine. This hydroxide is going to steal a hydrogen that is 1 carbon away from the chlorine. So it's not going to steal a hydrogen that's attached to the same carbon as the chlorine. It's going to be 1 carbon away. And so this hydroxide is going to steal this hydrogen, and we're going to make water.
That's just so it creates a double bond.
Yeah, and so this bond forms a double bond, and the chlorine gets kicked out because of it. This is very complicated chemistry. Yeah. Yeah. So you get a chloride ion, and what's left? This chlorine has gone. So what are we left with? We're left with 2 carbons, and what's attached to the first carbon?
2.
Just 2 hydrogens. What's attached to the second carbon? 2 hydrogens. The main point of this is we're starting with 2 things and we're ending with how many? 3. We're making a new thing, right? This is an elimination reaction. We're making an extra product. Also, we're starting with a saturated compound and we're ending up with an unsaturated compound, right? We're making a double bond. This is still an elimination reaction. But-2-ene is prepared from 2-chlorobutane in the presence of a strong base. So what that means is 2-chlorobutane. Let's draw out 2-chlorobutane. 4 carbons. What's attached to the second carbon in 2-chlorobutane? A chlorine. And there's hydrogens all over the place here, right? There's hydrogens everywhere. Blah, 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 blah. We're going to react this with a strong base. And so the hydroxide, I want to be very clear, it could react with a number of different hydrogens. Let's go 1 carbon away from this chlorine carbon bond. What's 1 carbon away? Do you want to go to the left or to the right?
Doesn't matter.
It doesn't matter, but it's telling you the product that we're going to make. So if we went to the left, this hydrogen would be gone, right?
Yeah.
So we would make a double bond between 1 and 2. That would be but-1-ene.
Okay.
So it's saying this hydrogen's leaving and this chlorine's leaving. So the hydroxide steals the hydrogen and it makes water. You have a chloride ion leaving as well, and then we're left with butene, and then just hydrogens. But again, the important part to remember is that we're starting with 2 things and going to 3 things. When we're making an extra thing, that's an elimination reaction, right? Hopefully that makes sense. Yeah.
You said we didn't have to be able to identify all 3 of these substances.
You don't have to tell me if something is a hydrohalogenation. You don't have to tell me if something is cracking, and you don't have to tell me if something is dehydration.
But is it expected when they give us the steps that we do the correct one?
Again, it's probably the most likely scenario is that they give you a reaction. And they say, either they'll say one of these things is missing, and they'll say predict the product, or they'll say what type of reaction is this? And so you'll have to understand, if they gave you the whole reaction, then you'll have to identify it as an elimination reaction. And I want to show you the types of diploma questions that you're very likely to see here when you're doing the diploma. So, yeah, you gotta go. So let's take a look at this. Take a look at the reaction and try and identify what kind of reaction is this. Is it elimination? Is it addition? Is it substitution? Is it some weird reaction we've never seen before? Yeah, we're going to talk about esterifications tomorrow. Yeah, go out on a limb and say it's not esterification. What? Okay.
So I got it.
Okay, let's take a look at this. Imagine you were in the diploma exam, Jordy.
I just got it right.
Imagine that you had actually seen all of this before. I guess you don't have to, but that's fine. Is this what? How many things are we starting with?
1.
1, and how many things are we getting?
2.
Elimination.
Yeah.
Right?
It's the water.
We're starting with something as saturated. We're making a double bond. That is elimination. So C and D are out. Okay. Now, last question. Nope. The acid, the sulfuric acid. Where do you see it? Above the arrow. What does that mean? It's a catalyst, and what is the only job of a catalyst? To lower the activation energy, therefore speeding up the reaction, right?
So it's A.
It's A.
Oh wow, look how I did.
Jordy, you were right.
I always am.
Yeah, you stumbled into the correct answer. Congratulations.
That was the thing yesterday. I had that one already.
Did we have this question already?
Yesterday.
Ah, son of a gun. Sanjana.
Why are there equilibrium arrows on question number 29?
Because it's in equilibrium.
Okay.
Because the reason why is if you leave the water there, the reaction can go backwards.
Okay.
What would happen if we dumped a bucket of water into this container?
It would go down.
We would increase the concentration of water, and where would the equilibrium shift? To make more of that,
All right. I
Yeah.
got you.
Okay. This question, equation number 1, is this addition, substitution? It's addition. Good. 2 things make 1 thing. Done.
B.
What the heck is this? Yeah. It's the one that's not good.
Remember, we haven't learned about esterification, but we have learned the other 3. So by default, right, Jordy?
Yes.
By default, we can stumble into the correct answer, can't we? On a numeric response question, the answer is B.
Yes.
Yeah.
You just tricked the scan shot and it gets confusing.
Yeah, that's right. I'm sure it would. Max, question about this?
No. I was just gonna say the answer, but
Okay.
One thing makes two. Want to get this pretty good.
Esterification makes sense. That's great. Okay. Let's take a look at this. Let's go one by one. Let's go one by one and let's try and identify. What? No, that's not. The first one. How many things are you starting with?
Two.
How many things are you ending up with? One. So what is that?
It's addition.
That's addition, right? You're starting with something unsaturated and you're going into something that is saturated. So that's an addition reaction. Good. Okay, one's out. Typically. Number two. You're starting with one thing and you're turning into two things. And what do you notice about this product?
double bond.
It has to be a double bond, right?
Yeah.
Or it's cyclic, but you can't have two things be cyclic, right? You need at least three things to be cyclic. So yeah, that's absolutely, what are we going to call that? Elimination. Good, two's out. Number three, do you agree that when I react this thing with bromine, it's going to kick out one hydrogen and replace it with a bromine? Some people like to call this replacement reactions, but it's not. Substitution reactions. By default, 4 is an esterification.
Now what is that?
Now, an esterification, I am going to give you a sneak peek, and then I'm going to give you time to work on your major assignment or whatever. Or I'm going to give you time to work on the assignment that was due today and ask me some questions. Okay, can I get you? Do you have any room on the bottom of your page? Yes, today. So stop talking and listen up.
Everybody shut up.
An esterification reaction is when you make an ester. And an ester looks like this. I'm going to draw a dot, 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 because it could start with anything basically, but it looks like this. It's C double bond O, double bond, or single bond O, carbon. This is what an ester looks like.
Okay, let's just
Now, what I want to bring your attention to is if you were to cut across this bond, you would end up with COH. What? And on this side, you would end up with COOH.
Question mark? Where's the question mark?
I'm curious. In order to bring these two together, in order to get this from that, this is what we call an ester, and it has very specific properties. You get an ester from a what? What's a COOH?
Carbonate.
No.
Carbide.
No.
Organic.
Carboxylic acid. Do you remember me saying alcohols and carboxylic acids kind of look the same, but they're completely different? Right? That thing. Good. So, if I were, what would I have to steal? What would I have to steal out of this combination to make that? If I wanted to go COC, what would I have to steal out of here?
2 hydrogens.
2 hydrogens.
One oxygen.
And one others. In which Kapow.
So what are you pulling out of here?
Water.
Water.
You're basically
Pulling,
dehydrating it.
you're dehydrating this. This is another dehydration reaction, except we call it esterification. That's what we're going to talk about tomorrow. Tomorrow, we are not going into the lab. Maybe. I don't know, maybe we'll learn about something. No, we definitely don't have time to watch any movies. That's for sure. Yeah, and so maybe we can learn a little bit about esters first, and then we can do making wintergreen. Wintergreen is basically a minty smell. It's a really vibrant minty smell. And that's why I wanted to do it before. I don't know, I'll make up my mind. Whatever.
Oh wait, it's the full up of
What's it doesn't like first?
Gonna make the French out of the baby.